Hey ladies and gentle lads, welcome to the Sixth Form Math Tutor channel. This is the first video on this channel, so if you have stumbled upon this video, congrats, you're either an OG that has been supporting me since the start, or you're just a panicking student that wants to look for last minute revision videos before their final exam. In which case, that's what I'm here for. I am your Sixth Form Math Tutor. I will be teaching you all these concepts, specifically for last minute revision practice. Let's get straight into it then. So, the first concept I would like to discuss first is the proof by contradiction. So let's start off by defining what a proof by contradiction is. So, a proof by contradiction, in short, is just a method of proving a statement false or true by proving its opposite false. The keyword here is opposite, and I'll be getting into what that means right now. So let's say you have a statement, 3n is not divisible by 4. If I want to prove by contradiction that 3n is not divisible by 4, what I need to do is I need to prove its opposite false. When I say opposite, I mean I have to prove 3n is divisible by 4. I have to prove this statement is false. So that's very easy. I can just say 3n over 4 is equal to some integer k. You get 3 over 4n is equal to k. Since n and k are both integers, k cannot be an integer because you're multiplying by a fraction, which is not an integer, so you're going to get a non-integer. So yeah, that's essentially how you do a proof by contradiction. So if you're doing a bigger kind of actual exam question that asks you to prove something by contradiction, what you're going to be thinking is you're going to have this statement. This statement is like true. So when you have that, what you want to do is you want to find out, okay, let's let the statement be false. So when you have a statement and you want to prove it false, let's say, take that example again, 3n is divisible by 4. This is your statement that you want to prove false. Then you're going to want to represent this algebraically because most of the exam questions are going to be writing it in a word form. So it's not going to be very easy to see where you have to go if you're just working off of the sentence or paragraph that they give you. You have to represent it in a mathematical way. So here we can represent this as 3n over 4 is equal to k, where n and k are some integer. So when you have this, then you're going to want to manipulate it, or if it's already in this form, then you can just come to a conclusion. You have to state that since, like, okay, let's just say 0.75, and this makes it a lot easier to see. We know that since k is an integer, it has to be a whole number. There can't be any decimals. There can't be any decimals. Just some simple statement like that. So therefore, k cannot be an integer, and therefore 3n cannot be divisible by 4. So now we've proved that this statement is false. So that contradicts this statement. That's where this proof by contradiction name comes from. So once we prove that, we can then say that this statement is true. Okay, so we're going to be looking at a common use case. This is one of the most famous uses of proof by contradiction, and is also likely going to be on your exam if there is a proof by contradiction question, because usually they will ask stuff about proving that a square root of a number is irrational. So technically root 2 is the most famous case, but this can be generalized to any square root of k. So I'm going to give you guys a few seconds to just look at this question, see if you can work on it yourself. Okay, so I'll be getting into the solution now. What we want to do first is we want to identify what our statement is that we're trying to prove. So we're trying to prove that this statement, root 2 is irrational. We have to prove that this is true. So since we want to prove that root 2 is irrational, we have to prove its opposite false, which is root 2 is rational. We have to prove that this statement is false. Now, we have to represent this algebraically, and we're going to look at the keyword rational. Now, a rational number, is a number that can be expressed as a fraction, a over b. This is a common definition that A-level and IB students both should know very clearly in their minds. So, by this definition, we can state that root 2 is equal to a over b. And one more thing is that a and b are coprime. Now this word coprime is a fancy word. It basically means that a and b do not share any common factors. So let's say 2 and 5. These numbers are coprime because they don't share any factors other than 1. So yeah, this is the main statement that we're going to be using as well to prove that this is false. So moving on to the next step, if we square both sides, then we get these two cancel out and we get a 2. Then we get this a squared and b squared because the square distributes into the numerator and denominator. So from here, we multiply both sides by b squared and we get 2b squared is equal to a squared. All right, now we can't really do much with this statement, so we have to deduce stuff now. And the first thing that I hope you guys can notice is that a squared is represented by 2 times b squared. So it's represented as a product of two numbers. And by that definition, a squared must be divisible by 2 and also by b squared. So from here, we can show that with the first statement, since a squared is divisible by 2, by the fundamental theorem of primes, which I'm sure some of you have heard of, since a squared is divisible by 2, this can be represented as a times a, and therefore a is divisible by 2. So from here we have one of our main statements. So we can work on our previous statement, what we've proved. Since a is divisible by 2, we can say that a is equal to 2 times some integer k. So from here, we know this is true because a is divisible by 2. So from here, we can substitute this into our above equation here. A squared is equal to 2b squared. So if we sub a equals 2k into here, we get 2k all squared is equal to 2b squared. We get 4k squared is equal to 2b squared. Divide both sides by 2, and we get 2k squared is equal to b squared. Now, by the same principle that we used for this statement, we can do it on this statement. We know that b squared is equal to 2 times k squared. Therefore, b squared is divisible by 2 and k squared. Now we're only going to focus on this one because by the fundamental theorem of primes again, we know that since b squared is divisible by 2, b must also be divisible by 2. So this is our second part of our statement. So We have A is divisible by 2 and B is divisible by 2. They both share a common factor. So they have a common factor of 2. However, this statement right here states that A and B are coprime, meaning that they don't share any factors. So, since we stated A and B are coprime, they cannot share any factors. So this contradicts our statement. And since this contradicts our statement, this statement must be incorrect. And therefore, since this is false, we've completed this step, which proves that this must be true. And so there is our statement proven. That is a very elegant proof, very beautiful. And yeah, this is a great way to practice your proofs by contradiction if you are still unsure about how to go through with this thing. And now I'm going to give you guys a little homework problem. So this question was from a past A-level paper. Very simple, 4 marks. Prove by contradiction that no integers x and y exist, such that 6x plus 9y is equal to 1. Feel free to pause here to take a screenshot or work on the solution yourself. Okay, I will now go through the solution just under here. So, we want to prove that no integers x and y exist, such that 6x plus 9y is 1. So we have to prove the opposite. We have to prove that there is an integers x and y exist. So 6x plus 9y is equal to 1. So by the statement, we can assume that this is true. And so we can work with this. We can take out a common factor of 3 on the left side, and we get 2x plus 3y is equal to 1. We divide both sides by this 3, and we get 2x plus 3y is equal to 1/3. Now, since we said that these x and y's are integers, so they have to be whole numbers. They cannot be decimals or irrationals. And so because we have this sum is going into a fraction, this fraction is not actually an integer. So, as we know, if we have two integers that are being added up and they're being multiplied by another integer, they cannot produce a non-integer. For example, if we let x is equal to 1 and y is equal to 2, for example, we get 2 times 1 plus 3 times 2. This is equal to 2 plus 6, which is equal to 8. This is way above 1/3. And it's an integer as well. And this works for any number, in case you guys want to try it out. And so therefore, since this cannot happen, since the sum of two integers cannot produce a non-integer, then this statement, the statement that integers x and y exist is false, and thus it is proven, basically. So technically we don't actually need that. We can just say do a box. And that's our solution complete. Yeah, I hope you guys enjoyed this video, and I hope you guys have good luck on your exams. And yeah, that's all I have to say. So, goodbye. I'll see you in the next video.